left-hand limit of a function, right? So am I audible?
Yes, sir.
Yes, sir.
There is a connection problem. Sometimes connection get lost. Anyway, so what last time we were talking about right hand limit, left hand limit, and we saw that the limit exists if and only if right hand limit and left hand limit exist and they are same. So this is one of the criteria to check the existence of limit of a function, right hand limit and left hand limit. So one more criteria which is useful to evaluate the limit is sandwich principle or squeeze theorem for limit, which we did for sequences similar to the sequences, right? So sandwich theorem or squeeze theorem. Suppose we have three functions f, g, h are functions from set A to R. A belongs to R is a cluster point of domain of these functions. Suppose f of x less than or equal to gx is this less equal hx for every x. For every x in domain. So gx is sandwiched between f and g. So if limit x tends to a, fx is equal to limit x tends to a hx, then and it is equal to L, limit of f and h at a is L, and this limit exists, right? Limit is L and it is finite number, so it exists. Then limit x tends to g, x tends to a gx also exists, and it is same as so it is what should be limit of g at a?
L.
Yeah, so it should be same as L. How to prove this? So geometrically, what this theorem says, A, this is point A, F. So this is function F, right? And Another function is so h. This is h and g. This is g. So green color function is g, red color is f, pink color is red color function is h, and pink color function is f. So for every x, you look at what is fx. Fx is here. What is hx? No. What is the largest function is hx. So yes. So this is hx. This is g. So gx is in between f, and at this x, what is hx? So if you compare values of this function at any x, values of this function at any x, then fx is less than or equal to gx is less than or equal to hx. Now, limit of f and h at a is same number L, then what is the possibility? G has limit at a, limit of g at a must be L. Right, that means G is sandwiched between f and h. Okay, so how to prove this? So what is our assumption? What is given? What is assumption? So first thing is fx is less than or equal to gx is less than or equal to hx for every x. This is the first thing. What is second point? Limit x tends to a, fx is equal to limit x tends to a, hx. And what is our claim? What is our claim? Limit x tends to a, gx is equal to same number L. Exist and it is L. How to do this? How to prove that limit of some function at some point is L? How to do this? Right? What is the natural way to do this? Yes.
Epsilon delta definition.
Right. So for given epsilon, we should produce delta. So how to start? Given epsilon, right? But we want delta. So we want delta such that whenever distance of x from a is less than delta, the distance of gx from L is less than epsilon. This we want. So in bracket. So given epsilon, we want this. But epsilon is given. So since the limit x tends to a, fx is L. So for this epsilon or above epsilon, because epsilon is given and we want to produce delta. So, but for this epsilon, by definition of limit, there exists some number, let us say delta 1, such that whenever distance of x from a is less than delta 1, then distance of fx from a is less than fx from L is less than epsilon. Right? Also, limit x tends to a hx is also L, right? And for same epsilon as above, there exists another number which is may not be same as delta 1, such that whenever distance of x from a is less than delta 2, distance of hx from L is less than epsilon. there are two deltas, right? So the delta, what's the required delta which we want to find? Delta is actually found the deltas. We have a required delta. Is from expression 1 a plus delta 1 a minus delta 1. Then in second step we found another delta. This distance is delta 2. This distance is delta 1. A minus delta 2 a plus delta 2. So for every x in this a minus delta 1 to a plus delta 2, second is true. For every x in a minus delta 1 to a plus delta 1, first expression is true, and therefore let what should be the delta, required delta?
Minimum of
Minimum of both.
delta 1.
Right. For minimum delta, both are true. Then, if distance of if x from a is less than delta, then what happens? Then, then is distance of gx, then distance of fx from L is less than epsilon, and distance of hx from L is also less than epsilon. Right, because it is minimum, both things are true. So whenever distance of x from A is less than delta, then it is less than delta 1 as well as delta 2. So that minus epsilon less than fx minus L is less than epsilon, and minus epsilon less than hx minus L is less than epsilon, which is same as L minus epsilon is less than fx is less than L plus epsilon, and L minus epsilon less than hx is less than L plus epsilon. For every x whose distance is less than delta, which is same as L minus epsilon is less than fx. But we know that for every x, fx is less than or equal to gx, and gx is less than or equal to hx. Whatever is x doesn't matter. And in particular for this x, hx is less than L plus epsilon. Right? So that's what we get from above discussion. So hence what is the conclusion? So hence the distance of x from A is less than delta, then L minus epsilon is less than gx is less than L plus epsilon. What does it mean? Minus epsilon is less than gx minus L is less than epsilon, which is equivalent to saying that absolute value of gx minus L is less than epsilon. Thus, what we found, given epsilon, we can produce delta, so that whenever whenever distance of x from A is less than delta, the distance of x from L is less than epsilon. So what is the conclusion? For every epsilon, therefore limit x tends to A, dx is right. So the proof is clear. Any doubt in the proof?
No, sir.
Okay. Now, how this proof is essential, because sometimes easily we can guess the limit. For example, let f of x is equal to x sine by x if x not equal to 0. Then prove that limit x tends to 0 fx is equal to 0. So we already know that this limit is, we have already proved it, but Using this quiz theorem, it is very straightforward. So note that this is the absolute value of f of x, x sine 1 by x. Right? What can you say about this absolute value? Is it less than absolute value of x? Am I right? For all x not
Yes, sir.
equal to 0. Fine. For every x, this is going to happen. Non-zero x. Therefore, can I say that is it true? Second expression. Is it true? Right? What is the situation? Absolute value of f of x is less than or equal to something. Right? Here we have right hand side is absolute value of x. This is true for every x. So absolute value of x is a number and absolute value of f of x is quantity inside the modulus, right? Which is same as we can say this is this alpha. The absolute value of f of x is less than or equal to alpha means minus alpha less than or equal to fx less than or equal to alpha. This is inequality, you know, right? Am I right? So
Yes, sir.
let let gx is equal to minus of this, hx is equal to this, and fx is equal to x sine 1 by x. Therefore, what is the situation? Gx is less than or equal to fx is less than or equal to hx for all x non-zero. Our domain is non-zero x. Fine. So second point, what is limit x tends to 0 gx? That means what is limit x tends to 0 minus of absolute value x? What is this limit?
0.
0.
0. And what is limit x tends to 0 of hx? That means limit x tends to 0 of absolute value of x, which is 0. And now compare, look at the previous inequality. Therefore, hence, the limit of g is 0, limit of h is 0 at 0. So what is the limit of f? What we expect?
0.
0. Hence,
0.
by sandwich principle, limit x tends to 0 fx, that means limit x tends to 0 x sine 1 by x. It is immediately we can observe the limit is 0. That sense sandwich principle is useful. Right? Okay, so let f of x is equal to f of x is equal to x if x is rational and minus x if irrational. Okay. Limit x tends to 0 f of x is equal to what? What do you think? What should be the limit? This limit x tends to 1 f of x will be the limit. x tends to minus 20, what should be the limit at 0 for this function?
0.
Does it exist? Okay, in this case it is 0. What is the limit x tends to 1?
1.
Limit x tends to 1 f of x. Does this limit exist? Because the rational function is x.
No, sir.
No. So here does not exist. Right? Do you understand why?
Yes, sir.
Right. So for such function, limit exists where value at rational and value at irrational. So as we discussed in the previous session, so rational values on y is equal to x line, at irrational values on the line y is equal to minus x. And where these two lines coincide, at that point only limit exists at 0. Here also limit does not exist. So point is if f of x is positive or greater equals 0, suppose function is positive for every x in a, right? Suppose function is greater equals 0 and a is a cluster point of a, right? Function is non-negative and a is a cluster point. So if limit x tends to a fx exists is equal to L exists, then can you say that L is greater equal 0?
Yes, sir.
Right. Limit is greater equal 0. Of course, if your function is strictly positive, then also limit is greater equal 0. Or if function is greater equal 0, then also limit. So can you prove this? If function is greater equal 0, then limit is greater equal 0. Can you see the proof? It is exactly similar to the sequences, right? So if our function is positive and limit at some number a is positive, function is greater equal 0, and whatever is your a, limit is also greater equal 0. Now, if you want to prove this, suppose limit is negative, right? Suppose function is greater equal 0 but limit is negative at a, then what will happen?
Sir, your voice is breaking.
Is it clear? Am I audible clearly now?
Yes, sir.
So suppose limit is not greater equal 0, what will happen? Just go back and recall the previous statements which we have discussed so far. So what would you say limit is not greater equal 0? You see what is the will happen? Suppose L is not greater equal 0, that means L is negative. Then you recall the theorem, if limit of function at point is negative, then there is a neighborhood in which function is negative. Am I right?
Yes, sir.
So f of x is negative for all x in a minus delta, a plus delta, x is not a. So what is the problem? Is it a contradiction?
Yes, sir.
So why this is contradiction?
Because fx is greater than equal to 0.
Right. So contradiction to the assumption that f of x is greater equal 0 for all x in the domain. But if we assume that limit is negative, then in some neighborhood function is negative, which is not true. Right? Function is everywhere given to be non-negative. Right? So this is a simple object. So, so if limit x tends to a, f of x is equal to L, then limit x tends to a, absolute value of fx is absolute value of L. This is true. Right? Correct? Am I right?
Yes.
Right. So if limit of f is L, then limit of absolute value of f is absolute value of L. That's fine. But converse is not true. That also we discussed. Now, if limit x tends to a, now we want to think about the power. So limit x tends to a, f of x is equal to L. And what can we say about limit x tends to a, f of x square? What should be the limit? Does this limit exist? Square of f. I am taking square of function f. That means when I say f of x square, means it is f of x into f of x. And from our previous discussion, what it should be?
Limit of f whole square.
Right. That means L square. This is obvious, right? This is obvious because when I say f of x square, means it is f of x into f of x. The limit x tends to a, f of x whole square is limit x tends to a, f of x into f of x. And we already know that the limit of f into g is limit of f into limit of g. That means it is L into L, which is L square. Forward. Can this be extended? So if n is a natural number, any natural number, right? That means n is greater equal 1. And limit x tends to a, f of x is equal to L. From this, can I say that limit x tends to a, f of x whole square, whole raised to n? What should be what I can write or what I can expect? I am taking nth power of fx.
L to the power n.
Right, L to the power n. It is obvious by induction. So, by induction. For every n, this is going to happen. Right? If it is for 3, for from 2 to 3, it is easy. From k to k plus 1 also it is easy. So, it is just use the n is equal to 2 case, that is from k to k plus 1 and check. So, but now we are interested in fractions. So, what we are interested in, what is limit x tends to a, f of x raised to half. That means limit x tends to a, root of fx. What can you say about this limit? What can you say about this limit? Yes. What is limit x tends to a, square root of fx. Do you understand what should be this limit?
Square root of limit of f.
So if you recall the result for sequences, then can we expect that this is limit of square root of limit of limit x tends to a fx square root of limit of square root is square root of limit. So, but is it so obvious? That means we have some, we should put some conditions on function f.
Yes, sir.
What condition we should put?
That fx should be greater than equal 0.
So fx is greater equal 0 for all x in the domain. And what should be the one more condition? Okay, so limit x tends to a f of x exists. Then limit x tends to a f of x exists. Then limit of square root of f is square root of limit. But here square root of L makes sense because by previous discussion we know that if f is greater equal 0, L is also greater equal 0. Therefore square root of L is well defined, no problem. Right? So how will you write down proof of this? How will you write down proof of what is given? Limit x tends to a f of x is equal to L. Right? And we know that L is greater equal 0. So this is our claim. Limit x tends to a square root of fx is square root of L. This is our claim. That is what we want. That is given epsilon, there exists delta, such that whenever distance of x from a is less than delta, then distance of square root of fx square root of L is less than epsilon. So this is what we want. You can also use the sequential criteria. That is also fine because here we are taking positive square root. So we can actually produce delta for epsilon or sequential criteria. Or what is another way? If xn converges to a, then what we want to prove? If f of xn converges to root n. Both things are true, same. By sequential criteria, if you choose any sequence xn converging to a, then look at square root of f of xn. If that converges to L, if it is true for any sequence, then we can say that limit of this function root fx is root n. Do you understand what I am saying?
Yes, sir.
Right. So which way is convenient? Uh, I will prove by second. You can suppose xn is a sequence in domain such that limit of xn is a. Therefore, since limit x tends to a f of x, we are assuming this limit to be L. We have this limit of f of xn. What should be limit of f of xn? If xn converges to a, what should be limit of f of xn? L.
L.
Right. Also, uh, f of x is greater equal 0 for all x in a, f of xn. xn is a sequence in domain, so it is also greater or equal 0. Therefore, we can think about the limit of this sequence square root of xn. It's just uh, n tends to infinity. And each fxn is greater or equal 0, I can talk about its square root. Then what is the limit of square root of fxn? Is it same as the limit of square root of limit of f of xn? Right? This is square root of. So it's true for any sequence that converges to A. Here we can conclude that it is hold for any sequence xn in A that converges to A. We conclude that the limit x tends to A square root of fx equal to square L. Okay, is this clear?
Yes, sir.
Now this is exercise or homework, you can say. Given epsilon, try to produce delta so that this is less than epsilon. And what is hint? The similar proof for sequences. You have proved the similar result for limit of sequences, and you just go back and see that proof. From that proof, you will get idea how to prove this. This is hint, right? This is exercise, and you try to prove in other way. This is the one way using sequential criteria. Okay, so the next point we want to
Sir,
yes.
can you just scroll up a bit? Yes, sir. Okay, sir. Thank you.
Now, if limit x tends to a f of x is equal to L, then we know that what is limit uh, x tends to a 1 upon fx. What is this? What do you think? What should be this limit? Yes. Yes. What should be this limit?
So 1 by L.
1 by L. But here we should make some assumptions. Otherwise, this is not well defined. So, what assumptions we should make? What assumptions we should?
Fx is not equal to 0.
So, in fact, fx is not equal to 0. But if fx is not equal to 0, it may happen that e, e is not in the domain, maybe whatever, and function is positive on this side of a and negative on this side of a. Suppose we put the restriction that fx is not equal to 0, but there is a restriction on L also.
Yes, sir.
L should not be 0. Then only we can think about 1 by L. But if limit of function at L is not 0, that means either it is positive or negative. So function is positive or negative near A, then only limit is possibly positive. So f of x is not equal to 0. for x is in A and limit extends L is also non-zero, right? Limit at A is non-zero, but then you can think about this. If limit is non-zero, limit exists at A and it is L and L is non-zero, that means near A function is positive or negative. That means L is positive or negative, whatever it may be. Then limit of 1 upon fx is 1 by L. So you should think about. So now I want to take this. Suppose we already proved this by sequential criteria, quotient, limit of quotient and quotient of limits. But what I am interested in is, so what is limit x tends to A, f of x is infinity, means what? What do you mean by limit of function at some point is infinite?
That it diverges to infinite.
Ah, means what? Means in epsilon delta definition, how to understand this, how to mathematically visualize this. By definition of epsilon delta definition means, so how to understand limit is infinity at some point. You want to understand this, but note that the limit x tends to a f of x is L and L is finite number. Means what? When we say limit at some at A is some number L, means what? How will you understand this? The given epsilon, there is delta and so and so. Correct? Yes.
Yes, sir.
Given epsilon, there exists delta such that whenever uh, x is in delta neighborhood of A, we have f of x is in epsilon neighborhood of L. Right. That is, this is same as whenever distance of x from A is less than delta, then distance of f of x from L is less than epsilon. Saying that, this amounts to say that if x is in delta neighborhood of A, then f of x is in epsilon distance from of L. So same thing. This is what our understanding of limit. But now we are thinking about what is limit of function at is infinity. So we want to understand this, right? If limit is finite number, that is fine. Now, do you understand what needs to understand before understanding limit is infinite? So when we say that limit at A is L, then we think about two neighborhoods. Which neighborhoods? We think about two neighborhoods. Which neighborhoods?
Delta and epsilon.
Delta neighborhood of A and epsilon neighborhood of L. So if L is equal to infinity, then what is this epsilon neighborhood of infinity? is epsilon neighborhood of infinity. What do you think about epsilon? How will you look at epsilon neighborhood? Here we think about epsilon neighborhood of L, but here now in our case limit is infinity, suppose. And what is epsilon neighborhood of infinity? How will you deal with this? How to understand this? That's the question, correct? Problem is clear what I am saying.
Yes, sir.
Okay, so if you look at real line, where is infinity? At the end, right hand side, right end of the real line, there is infinity, correct? So how will you deal with how will you look at the infinity, or how will you visualize the epsilon neighborhood of infinity? If this distance is epsilon, so this is a convention, you can say. So everything on right side of epsilon, everything is on right side of epsilon. So is x such that x greater than epsilon. Is it clear? Everything which is on the right side of epsilon is a neighborhood of infinity that you can see. You can understand what I am saying?
Sir, can you please repeat this part?
Yeah. Why I am interested in epsilon neighborhood of infinity, it is clear. Why I am interested in epsilon neighborhood of infinity, it is
Yes,
clear.
sir.
Okay. Now, where is infinity? It's on the right end of,
Right.
right. So suppose epsilon is this number on real line. Then what is the region which is closer to the infinity? That means neighborhood of infinity. Everything is on right side of epsilon. It is, it is,
Yes, sir.
it is the region which is, we can say it is closer to the infinity in some sense. Because what neighborhood we are taking? Suppose you take neighborhood of 1 kilometer area around your house. It is your neighborhood. That is our assumption. Okay, this is my neighborhood. 1 kilometer away, you choose your house as a center and draw a circle of radius. Right? You can think about your house as a center and you draw a circle of radius 1 kilometer. You can say this is neighborhood. But sometimes you say that you take your house as a center and draw 10 meters circle around you. That is your neighborhood. So it depends on. Similarly, if everything is on right side, if you consider everything on right side of epsilon, that you can think about as a think of neighborhood of infinity. Am I right?
Yes, sir.
Fine. So, and therefore, to the view of this definition of limit, and if limit is infinity, how will you make the definition of limit x tends to a f of x is infinity? Can I say that this is e epsilon infinity, epsilon neighborhood of infinity? Yes.
Yes, sir.
So how will you make the definition? But here epsilon is generally, conventionally, epsilon is used for the smaller quantities, right? Very small, infinitesimal quantities. If you want to go closer and closer to the infinity, you should choose some bigger number. And we go and look at the region near infinity, right? So conventionally, or roughly speaking, make the definition limit is infinite. So how to make the definition? Limit x tends to a f of x is infinity if, right? Now can you tell me the definition of limit at a is infinity? If,
Given
you tell
epsilon greater than 0, we can
uh-huh,
find delta such that f of x is greater than epsilon.
given epsilon, there exists delta such that whenever distance of x from a is less than delta, then distance of f of x from infinity, that means f of x is greater than epsilon. Does it make sense?
Yes, sir.
Right, because f of x is greater than this particular epsilon, that means f of x is in closer in the due to our convention or we use epsilon for smaller quantities and m for larger quantities. So I will change my notation here. So given any larger m, there exists delta. Any larger m, there exists delta such that whenever distance of x from a is less than delta, then distance then f of x is greater than m. Is it clear? Does it make sense?
Yes, sir.
Fine. This is the definition that limit is infinity. Okay. Example. Prove that. Limit x tends to 0 from right side of 1 by x. Idea is clear?
Yes, sir.
Now, same thing, limit x tends to a f of x is minus infinity. If, now you should tell me what is the definition, how to make the definition. Limit at a is minus infinity and minus infinity is on the left end. It is at left end of real line. And so, what is the neighborhood of minus infinity? Everything after this. Everything after some point. Correct? So how will you make the definition that limit at a is minus infinity? If given a positive m, there exists delta such that whenever distance of x from a is less than delta, then f of x is less than minus m. Does it make sense?
Yes, sir.
Yes.
Right. So, see, if you can you visualize the definition, or can you imagine the definition, or can you imagine the
Excuse me, sir.
yes,
Sir, why are we taking minus m? We can take m also.
because I am taking m positive. Whatever larger m positive you take, minus m is equally larger negative, right?
Yes, sir, but positive number can also work as a neighborhood of minus infinity, no?
No. We want to go into the neighborhood of minus infinity. For example, you look at 1 by x and on negative side. Right? Positive number doesn't
Yes.
help us. Positive m doesn't help us. For example, uh, in case of f of x is equal to x sine 1 by x. If I take epsilon is equal to 100, in this neighborhood there is no question of limit, because whatever delta you select, f of x minus 0 is less than 100, that happens for sine x sine 1 by x. Right? So larger epsilon is not a problem. Problem is what happens near, that means smaller epsilon. We understand, we are interested in smaller epsilon. At the same time, when we say that limit is minus infinity, so what happens for smaller neighborhood of infinity, minus infinity? Smaller means we should choose a very large negative. So that will be very close to minus infinity. That is the idea.
Okay, sir.
Right. That means we want to go closer to minus infinity. That means we should have very large negative. So that I am choosing large positive, so its negative is very large negative. Yes. Okay, so
Okay,
this
sir.
is idea. So we'll stop here, but before that, now I am interested in what is limit x tends to a f of limit x tends to infinity f of x is L. How will you make this definition? Limit x tends to minus infinity f of x is L, right? Limit x tends to infinity f of x is infinity. How will you make these definitions or how to understand these limits? This is a question. This we'll do next time, and we'll stop here. But in the our first stage practical session, we'll try to solve more problems on limit because during our lectures we did not solve many problems or applications. So that practical session we'll discuss practical on limit and applications of all these basic results, right? So that you can understand many ideas. Detail. Okay. So any doubts?